right, since we forgot to start the recording at the beginning, and I blame all of you. So just repeated use of our integration by parts. Why do we use that? When do we use that? When I get to this point and I still cannot just do the integral. Can't think backwards through. It's not a power rule. It's not just a direct antiderivative. So we apply that integration by parts a second time, which was what in the green here. Work our way down. Don't forget plus c at the end. Okay. Now, a lot of the ones that we have done this on have involved a polynomial. And so what we're going to look at today is there is actually a second option. But it only works on that one case where there is a polynomial as one of the functions inside of your integral. So it's called the tabular method. And you can see up there I do have the clarification. This only works if one of our functions is a polynomial, which x squared is. Okay. Now, the tabular method is a little gimmicky. If you can remember the gimmicks behind it, it's a great, slick method that could save you a ton of space and work, especially if we have those like higher order polynomials, if we were going to have to do integration by parts multiple times. But if you don't remember the gimmicks behind the tabular method, you won't get to use it, which is why we're going to practice it a couple times because it's pretty nice. Okay, so I would pick, this is the exact same example we just did on the last page. We already know what the correct answer is, so we've kind of already proven that the answer we get at the end of this is correct. What you're going to do is you're going to pick to separate your two functions. The first one that you pick, the one that I will put in the first column, which if you look at your book, they identify them as like f of x and g of x, just the two different functions in there, is going to be the polynomial function. So the very first one needs to be the polynomial function, like we would have picked for u. And the one in the second column will be whatever other function is in there. I'm basically creating two columns here. The first column, we will go through the process and take the derivative of this until we get to 0. The second column, we will just continue to take the integral, or to integrate. Try that again. Integral. Each time until we match the number of rows that first column has. So let me show you what I'm talking about. Our first polynomial is an x squared. Its derivative would be 2x. And I just keep taking the derivative. So the derivative of 2x would be 2. Take the derivative one more time. The derivative of 2 is 0. Once I finally get to a 0, you're done with that column. The other column, we just match that. So I need to have a corresponding term to each of those rows. So we already talked through this, but the integral of e to the 2x is 1/2 e to the 2x. So I'm doing my antiderivative in this second column. So then I do that again. So again, the antiderivative of e to the 2x is 1/2 e to the 2x, and I already have a 1/2 out front. So it ended up being 1/4 e to the 2x because 2 times 1/4 is 1/2. I do the antiderivative again, and I get 1/8 e to the 2x. Stop when I've matched the number of rows as the first column had. Okay, and here's the, again, a little bit gimmicky part of this is now we're going to multiply in diagonals. So I'm going to take my first term of that first column and multiply diagonally, multiply diagonally, multiply diagonally. Your diagonals need to alternate signs. So this will be a positive, a negative, a positive. We'll add that term, subtract that term, add that term. Okay. So our end result, x squared times 1/2 e to the 2x is 1/2 x squared e to the 2x minus 2 times 1/4 is 1/2 x e to the 2x plus 2 times 1/8 is 1/4 e to the 2x, And as with everything else we do, plus c. Some people love tabular method, and you can use it every time that one of your two functions in there is a polynomial. But you got to remember the gimmicks behind it, or it's not going to work. I think it would work. You have to be able to integrate. Yeah. Mm-hmm. Yep. Multiple times. Other questions? And so if we flip back to the last page, you can see that that's the exact same answer we got, right? Saved us a little bit of room on work, kind of. So let's try the tabular method one more time, just to go through. This one we would have had to do our integration by parts several times, like 3 times. So then tabular method becomes an even better option because, again, doing integration by parts 3 times becomes quite a bit of work. So our first column, we will let be the polynomial function x cubed. Our second column, we will let be the other function in there, which is just a sine x. Remember, your first column, we are taking derivatives. Second column, we are taking the integral, or integrating, or finding your antiderivative. So down my derivatives column, we would have power rule here. So 3x squared, 6x, 6, and 0, and we stop when we get to 0. And then you got to be careful with the sine and cosine stuff and positive and negative. Remember, guys, we're finding the antiderivative. Okay, so not the direction of a derivative. So if our current function is sine of x, what's its antiderivative? Negative cosine of x, right? Got to be careful with the positive negatives. So now going from negative cosine of x, what would its antiderivative be? Negative sine x. Okay, the antiderivative of negative sine x, cosine x, and the antiderivative of cosine x, sine x. Cautious with your positives and negatives. Okay, I'm going to pause there. Any questions on any of that? Okay, starting at your top, in the function in the derivatives column, we go in diagonals all the way down and alternate signs, positive, negative, or add, subtract, starting at always at add, okay? So although I am adding this first term, the negative cosine as I multiply will give me a negative term. So negative x cubed cosine x. On the next diagonal, I have that I'm subtracting it, but it's also got a negative in it. So minus and negative becomes plus 3x squared sine x. Next diagonal is just all positive, so plus 6x cosine x and minus 6 sine x. And if I were to stop there, what's wrong with my answer? Plus c. Questions? All right. The last one I have for us today is this, and I want to look at the directions and how I know that I'm doing integration by parts twice, and the little trick that's going to happen on this one. It says electrical engineering uses integrals that involves 2 integrations by parts and solving for the unknown integral. And that is something we really haven't done yet in the way we're going to do this one, and you'll see why it becomes a thing in the middle of this problem, but we're going to have to show our work slightly differently than we are used to. So use integration by parts. We know by the directions above we're going to integrate twice by parts. To solve for the unknown integral. So at the end of this, you will have your unknown integral equals. So you will have the integral of e to the x cosine x dx equals, and we will have then our answer after that, okay? So let's start with doing our integration by parts. First of all, I know tabular method's not an option because neither of those are polynomials, right? As I think through Lipit to think about doing my integration by parts, do I have a natural log up there? No. Do I have an inverse trig up there? No. Do I have a polynomial? No. Do I have an exponential? Yes. That's where I would pick u to be the e to the x. Which means dv dx equals cosine x. So follow my normal integration by parts rule here. The derivative of e to the x is e to the x. And my antiderivative of cosine x is sine x. So what I'm going to do is I'm going to come over here and say that this and then equals my integral of e to the x cosine x dx equals, and then do my integration by parts here, which would be, let's see, e to the x sine x minus the integral of e to the x sine x dx. Questions so far? We knew that we were going to have to do integration by parts twice, which is showing up right here, right? Now I'm going to do that integration by parts a second time. We already had this conversation. I'll pick u to be e to the x because of Lipit, which means dv dx equals sine x. And the antiderivative of sine x? Negative cosine x. All right. So coming in here, I'm going to now integrate that by using my integration by parts. All right. So u is e to the x, and times v is negative cosine x, so negative e to the x cosine x. Minus the integral of, and this is where this one starts looking kind of like we're running in circles here. So I'm plugging in v, which is negative cosine x, so I'm going to slide that negative out front. And I'm also plugging in the e to the x dx, so e to the x cosine x dx. Okay. Okay. Well, I'm not getting rid of the integral, and it seems like that's just going to be a continuous, like, change it from sine to cosine as I go line to line, right? But this right here is this right here. Okay, and so this is the little trick we're looking for. At some point, that integral is going to match, which means I can move them to the same side. They are like terms. I do need to distribute this negative through, so that's where I'm going to go next here. Okay, but guys, it's like solving an equation. If I am subtracting this integral over here and I want to move it to the other side of my equation, I would add that integral to both sides. Right? And if I have one here plus another one here, we end up with two of those integrals. And finally, I'm supposed to, as it says up there, solve for the unknown integral. Well, right now it's 2 times the unknown integral, so solving for that, I just divide by 2. Now, 2 things on this. I could totally leave it like that, minus the 1 error in my answer. I can also look at taking out the GCF, which is a very common way that you would see like a multiple choice option. Well, the GCF is the fact that they both have an e to the x in them, and they're both being divided by 2. So I can pull that 1/2 out front, and I can pull the e to the x out front. But what else do I need to do? Always. Questions? So when this is the topic, when this is the way the question is worded, when it says solve for the unknown integral, basically you get in this infinite loop of doing our integration by parts, and this would never go away, right? We can see that that's never going to go away. But as soon as it matches the original side, that's when you're key to bring that integral and get all of your integrals onto one side. And now we can solve for it, and that says that integral equals, and we have our answer. Questions on that? All right, so assignment then tonight. I have helped guide you through your assignment, broken it down section by section. You're on 351 doing 17 through 28 all. On 17 through 20, it's like the last example we just did. Okay, so solve for the unknown integral. 21 through 24, use your tabular method. Try it out. And then on the 25 through 28, figure it out. Use either integration by parts, your tabular method, solve for the unknown integral, whichever method you see would fit best with that problem or your brain. Use that.